Hi everybody. It's great seeing you. The title of my lecture is the Cascade Conjecture. So I think it's particularly appropriate for the Cascade lecture in Combinatorics. The Cascade Conjecture, Tverberg's Theorem, Topology, and the Four-Color Theorem. And please feel free to ask questions. Now I'm sharing the slide, but I don't see anything besides the slide. So I don't know if this is what I want to have, but probably it is. But okay, no, I think there's no alternative. Okay. So if you have questions, please interrupt me by shouting or something like that. And so some of the things I will talk about are related to what can be called combinatorial convexity. And here are three books and one paper that I can recommend as some general background. The most recent book is by Imre Barani, which is called Combinatorial Convexity. There is a book by Jerzy Matuszek, Lecture on Discrete Geometry, and another book by Jerzy Matuszek using the Borsuk-Ulam theorem. And all these books are dealing with topics which are related, of course, much wider than to my talk. And another paper is a paper by Imre Barani and myself, which is called the Helly-type problem. So about 15 years ago, I gave a lecture in some conference dedicated to Paul Erdős, maybe 100th birthday or something like that. And I gave a problem lecture, and then I thought it would be nice to write problem papers like Erdős used to write. So I have several, I made a mistake. I think Erdős mainly wrote about his own problems. He has quite a lot of problems, so he had no problem with that. But once you try to write also about other people's problems, then it becomes trickier. So I wrote one paper about Borsuk type problems and one paper with Imre Barani about Helly type problems. And I hope there will be further collections of problems. But here are the three books I mentioned, and here's a picture from 25 years ago of me and Jerzy Matuszek and me and Imre Barani. Okay, so let me jump right to Tverberg's theorem, which is in some sense the star of the evening. And it is a very beautiful theorem. Tverberg proved in 1965 the following. Let V1, V2 up to Vm be points in Rd, and suppose that M is greater or equal to D plus 1 times R minus 1 plus 1. Then there is a partition S1, S2 up to Sr of a square bracket M, this is the set 1, 2 up to M, such that the convex hull of Xi, I belong to S1, intersection the convex hull of Xi, I belong to S2, intersection and so on, intersection of the convex hull of Xi, I belong to Sr, is non-empty. Now, the case R equal 2 is called Radon's theorem, and it was proved in the early 20th century by Radon. Radon's theorem says that if you have D plus 2, yes, we can compute it, D plus 1 times R minus 1, so D plus 1 plus 1, D plus 2 points in Rd, you can divide them into two sets so that the convex hull intersect. To prove Radon, the proof of Radon's theorem is very simple. You simply write the non-zero affine dependence, or you write the affine dependence for the point. Since there are D plus 2 points in Rd, they admit an affine dependence. Namely, you have a some lambda I xi equal to 0 and some lambda I equal to 0. and then you just move the negative lambdas to the other side of the equation. And this gives you a convex combination of one part of the points, which is equal to convex combination of other part of the point. So this is just very basic linear algebra. And contrary to that, Tverberg's theorem, when R is bigger than 2, is a much more complicated mathematical statement. And Tverberg gave a proof in 1965. And I remember I was very, very impressed by this proof that I learned as an undergraduate. And I was so impressed that when I took a trip to Europe at the age of 24 after my service, and I decided to include Tverberg as one of the tourist attractions. And indeed, I visited Tverberg at his home in Bergen, and since then we met several times. And he told me about a direction that I also thought about, which is topological analogs of Tverberg theorems, which I'll mention a little bit later. And yeah, so this was fun. And Tverberg himself found another proof. So the first proof of Tverberg is based on the following idea. You put the points in very specific condition, which is called the cyclic condition, or you put them on the moment curve, and then the assertion of Tverberg theorem follows from a simple argument, and then you start moving the points around, and you make sure and you prove that whenever something get wrong, you can fix it. And the Tverberg original proof was very complicated, at least to my taste. Recently, Imre Barani wrote, and this appeared in the Israel Journal of Mathematics, a version of the old proof, a new version of the old proof, which is very enlightening and much simpler. In any case, in 1981, Tverberg found another proof for his theorem, and his proof was inspired by a result which I'll mention a bit later, the colorful Kara-Teodori theorem. And it was based on considering all partition of the vertices and looking at the smallest distance between one convex hull and the intersection of R-1 convex hull, assuming that this smallest distance is bigger than 0, and then using some geometric argument, which was still quite complicated to find a contradiction. And in fact, when I was a young faculty, I gave a seminar and I presented this proof, this 81 proof by Tverberg, and it took me 4 two-hour lectures. And at the end, I think I was the only one, or at most I was the only one who followed all the details. And but it was I think a simpler proof. In 1993, I visited the Mittag-Leffler Institute in Sweden, and I met Helge Tverberg, and I remember his 2 earlier proof. I asked him, Helge, do you have another proof for your theorem? And Helge said, yes, I have another proof, and this was proof with Vertica and Sinica Vertica, and this proof was much simpler. It would take about an hour and a half to present it. At the very same day, I met another mathematician, Sarkaria, and he told me, Gil, I know you like Tverberg's theorem. I found a very simple proof, And indeed, he found a proof that can be presented in maybe 40 minutes from scratch. I will not present the whole proof, but I'll present the basic argument. And this is Sarkaria proof. And the first ingredient of Sarkaria proof is this colorful Kara-Teodori theorem of Barani that I will now state. So let A1, A2 up to AD plus 1 be sets in RD, and suppose that 0 is in the convex hull of A1, the convex hull of A2, and so on, and the convex hull of AD plus 1. Then we can choose points, little a1 in big A1, little a2 in big A2, and so on, little AD plus 1 in big AD plus 1, such that 0 belongs to the convex hull of these points. So this is called colorful Kara-Teodori. If all the sets are the same set, then this reduces to the old good Kara-Teodori theorem, which asserts that a point in the convex hull of a set is already in a convex hull of D plus 1 or less points from this set. So, but I should say the proof of Kara-Teodori, the colorful Kara-Teodori theorem, is different than the proof of Kara-Teodori theorem. The proof of Kara-Teodori theorem is very basic linear algebra. Here we need slightly a more complicated, conceptually more complicated argument. We look at the closest point to 0 in this convex hull, and then we show, and I will not tell you the full argument, we show that if the closest point to 0 of this form has some positive distance from 0, then first we show that we can realize it as a convex. We can, in the convex hull expression, we can take away one of the points. So we can show that the minimal distance is realized already in the convex hull of D out of this D plus 1 points. This is step 1. And then we show that this other point that we don't need, we can replace it by another point from the same set to reduce the distance to 0. So this two assertion give you a contradiction that the minimal distance is bigger than 0, and this gives you the colorful Kara-Teodori theorem. It also gives you some sort of an algorithm, but unfortunately, this algorithm can be very non-efficient, and it is an open problem to find a polynomial algorithm for the colorful Kara-Teodori theorem, and or to show that it is hard in some computational complexity class, and there are a special set of computational complexity class by Papadimitriou that are suitable for this kind of problems, but I will not get into it. Okay, so this was a colorful Kara-Teodori, and now we go to the proof of Tverberg theorem. We organize we have D plus 1 times R minus 1 plus 1 points. We organize all the points instead of being in RD in a vector space V, in a vector space H in RD plus 1. This vector space is all the points in RD plus 1, so the sum of coordinates is 1. And then we take another vector space of dimension R minus 1. And in this new auxiliary vector space W, we let W1, W2 up to WR be R vectors spanning W whose sum is 0. And now we take the tensor product. And if you don't feel comfortable with the tensor product, you can just think about it as a multiplication of vectors, but so that you get a matrix. So you can just think about if you have a vector V tensor vector W, you can think about it as the matrix whose ij entry is Vi times Wj. Okay, and now we consider the following sets, S1 up to Sm. So remember, now we consider the tensor product of V times W. So the tensor product of V times W is a vector space of dimension D plus 1 times R minus 1. And in this vector space, we consider D plus 1 times R minus 1 plus 1 sets. So we are precisely in the setting of the colorful Carter-Odori theorem. And the sets we consider are the following. The first set is V1 tensor Wj, J from 1 up to R. So V1 tensor W1, V1 tensor W2, up to V1 tensor WR. The second set is V2 tensor W1 up to V2 tensor WR, and so on and so forth up to the mth set, which is Vm tensor Wj, J from 1 up to R. Now, one thing to observe, if we sum up all the elements of S1, we get a V1 tensor W1 plus W2 plus WR, which is 0. So 0 is in the convex hull. In fact, it's the barycentric center of all these sets. And now the colorful Carter-Odori theorem tells us that we can choose one vector, one such tensor from each set, so that 0 will be in the convex hull of the chosen tensor. And you see that the choices we make give us naturally a partition. And this was, by the way, this was the dream of many people who thought about Tverberg's theorem. You know, the proof of Radon's theorem used the fact that we have positive numbers and negative numbers. We can move to the other side, the negative numbers. We want something with R types of numbers, and this, in some sense, do the trick. So this gives us the partition, and a simple calculation tells us that 0 is indeed in the convex hull of this gives you a Tverberg partition for our points. Okay, I want to mention now an application for Tverberg's theorem, and in fact, I want to talk to you about the Turan ladder, and it is the following question. We consider an R uniform hypergraph on n vertices, and suppose that G has more than k minus 1 times n choose m edges. And then we have 3 theorems, and it's nice to compare them and to compare the methods that are used to prove them. Now, here we move to an area of combinatorics, which is extremal combinatorics. The general theme is we have a hypergraph with n vertices and certain amount of edges, and we want to know what is the minimum amount of edges which guarantee a certain sub-hypergraph. And the Turan-Mentel theorem about the number of edges which guarantee a triangle is a very old theorem of this nature, and therefore such theorems are often called Turan-type theorems. And there are really many Turan-type theorems of various kinds. And here let's consider the following sub-hypergraph that we want to achieve. So, okay, so I tell you 3 theorems. One says that if you have more than k minus 1 times n choose m edges, then G contains a sub-hypergraph, H. So every set of m vertices is either included in no edge, or it's included in at least k edges. This is statement number 1. this statement follows with slightly better bounds using the so-called polynomial or exterior, either the polynomial or the exterior algebra methods. The second theorem says that G contain K sub-hypergraph, H1 up to Hk, such that for every set S of M vertices, such that every set S of M vertices is included in no edge of each or in at least one edge in each. So for every set of M vertices, either this set of M vertices is included in an edge in each of these Hi, or it's not included in an edge in any of them. Now note that B implies A, because if we take the union of this H1 up to Hk, we get the assertion of A. And the proof of this result follows from Tverberg's theorem. You associate to the edges to each edges, you associate the characteristic vector which tell you which are the M subsets contained in this edge. So these characteristic vectors give you a configuration of points, and on this configuration of points, you apply Tverberg's theorem. There is another theorem which is the following, that under the precisely same condition, G contains a sub-hypergraph H such that for every set S of M vertices, every set S of M vertices is included in 0 modulo K edges. Now, this result is also stronger than the first result, because if it's contained in 0 modulo K edges, then it is included in no edge, or it's included in at least K edges. So this is a stronger statement, and the proof of this statement, for this statement, the bound K-1 times n choose M is sharp, and this statement follows using the Chevalley-Warning theorem. It's not known, for all the parameters. In order to apply the Chevalley-Warning theorem, you need that K will be a prime power. And if K is not a prime power, then this result is not known. Okay, so this was an example how this results in how there are various avenues to very similar results in extremal hypergraph theory, and it's interesting also from the computational point of view. The first proof does not give you an algorithm. Actually, I think no. No, the first proofs give you a randomized algorithm, a randomized efficient algorithm to find this hypergraph. A deterministic algorithm is not known. The second proof does not give you an algorithm because we don't know an algorithm for Tverberg's theorem. I think the bottleneck is an algorithm for colorful Combinatorics theorem. Once we have colorful Combinatorics theorem, as you see, we need to do some linear algebra, but we don't have an algorithm for that. And the Chevalley-Warning theorem, it's also, there's no known efficient algorithm, and it is quite plausible that none exist. Okay, so beside, let me also, just 1 minute, I will also enter with another, I'll add one participant I will add one participant to the audience by entering also from another computer, so I can see you. Okay, let me see how it works.
Make sure not to connect on audio on the second device.
Yeah, okay, but I'm not sure it works. Okay, let's see. Yeah, I will not connect on audio, no audio. No, I don't have audio. Yeah, good. So I will now again, good, good. Okay, so now I can see you, which is somewhat more pleasant. Okay, so so as you may know, I also have a blog, and I wrote maybe 16 years ago about 7 problems around Werber's theorem, and I think let me quickly go over them. The first problem is Eckhoff's partition conjecture. This was a very bold conjecture by Eckhoff. For several decades, Eckhoff, I don't know, some of you probably knew Jürgen Eckhoff. He was very pedantic, and for several decades he refused to even concede that this is a conjecture, but eventually he did. Very bold conjecture, and the idea was to try to make a purely combinatorial argument for Tverberg's theorem from Radon's theorem. This was disproved by Boris Book in 2010, and I think it's still exciting if there are some positive results in this direction, and there are few. The other problem is the cascade conjecture that I will talk about today. I will also mention another very interesting problem. It's sometimes called Sarkaria's Dutch cheese problem about the minimum number of Tverberg partitions. This both the second and third problem are completely open. The fourth problem, the topological Tverberg conjecture, this was an attempt to generalize the Tverberg theorem from linear to nonlinear, from linear maps to continuous maps, and this was known when the number of parts is prime power. And it turns out to be false. This was a big surprise about 10 years ago. There is the ray relaxed Tverberg condition that I will not talk today, and also not about the colorful Tverberg theorems. And I already mentioned the computational complexity of Tverberg's theorem, whether there is an efficient algorithm for it. Okay, so let me mention briefly some development about the minimum number of Tverberg partitions. And there is a very nice conjecture by Sirksma that asserts that the number of Tverberg R partition of a set of R minus 1 times D plus 1 plus 1 points in RD is at least R minus 1 factorial to the power D. Here is an example of equality. You take R minus 1 copies of the vertices of the regular simplex. If you don't like to have the same point twice, you can move them a little bit. And you take 1 point in the center. And in this case, the only type of Tverberg partition is to take the simplices as R minus 1 parts and the center as the last part. But the simplices, you have various permutation, you can take the points in this way. So if you fix which are the parts according to one vertex of the simplex, you have R minus 1 factorial permutation for each of the so altogether you get R minus 1 to the power D. And now it turns out that okay, so the first result is the result of Moshe Weik. It's a very interesting result. So at some point I think Micha Perles asked, can we prove a stronger theorem like Tverberg's theorem when we restrict the type of partitions that we want to get? And Moshe White proved that the answer is negative. For every partition of the numbers A1 up to AR, so that AI is between 1 and D plus 1, there exists a set in RD of n points such that every Tverberg partition of X induces the same partition on N given by the parts A1 up to AR. So this was a nice theorem, and as a bonus, Moshe White got that the number of Tverberg partition is precisely R minus 1 factorial to the power of D. So his example all have the same type of Tverberg partitions, and the number was the minimum number. Now, this followed by very nice result, which I will only give you a brief overview. And one result is by a book, Law and Nivash, from 2017. They consider a tree-like R-uniform simple hypergraph with D plus 1 edges and D plus 1 times R minus 1 plus 1 vertices. And for such a hypergraph, they associated points in RD, and the Tverberg partition correspond to rainbow coloring of the hypergraph. And also in this larger class of examples of configurations, the number of rainbow coloring, which is the number of Tverberg partition, is precisely this number R minus 1 factorial to the D. And then later, they identified some very nice hypergraph and conjectured that it is universal in the sense that for every large enough set of points, there is a subset where the Tverberg behavior corresponds to this special hypergraph. And this universality result was proved by Attila Por in very remarkable paper. So I just illustrate the situation. Here you have the tree-like hypergraph. So they are drawn on the left. So I will not define it, but you can make the definition yourself. So you see here 5 examples of tree-like hypergraph. Here you can see their example of rainbow coloring. This every edge is colored by 3 colors. Every rainbow coloring corresponds to a Tverberg partition. Sometimes all the rainbow colorings give you the same size of parts, but this is Moshe White's types example, but this is fairly rare. And sometimes they don't. This example number B is precisely the universal example, and the example number D is precisely the example we start with the simplex R minus 1 times and a point in the middle. Okay, now I want to move to the center of the lecture, which is the Cascade Conjecture. And it goes as follows. So the Cascade Conjecture is about Tverberg's theorem, and it is a statement which is mainly important if the points are not in very general position, but in very special position. So here is the conjecture. Given a set of points, a set X of points, X equal to X1 up to Xn, let TR of X be the set of points which belong to the convex hull of R pairwise disjoint subsets of X. So TR of X can be considered as the set of Tverberg points of order R. And here we may allow repetitions. Okay. So T1 of X is just the convex hull of X. And T2 of X is the set of all radon points of X. T3 of X is the set of all Tverberg points for 3 parts of X. And let's write TR of X, or TR bar of X, to be the dimension of TR of X plus 1. So if there is no Tverberg point, then TR of X, if there's no Tverberg point of order R, then TR of X is 0. If there is a Tverberg point, then TR bar of X is greater than 0, and it is equal to 1 if the dimension of the Tverberg point is 0. So they are just isolated points. If the Tverberg points are one-dimensional, then TR of X bar is greater or equal to 0. And then the cascade conjecture asserts that if we take T1 plus T2 and so on plus Tn, this is always greater or equal to X. And here in the statement, there is no mention of the dimension of the space we live in. So this is a sort of this type of statement. And it has the feeling of some algebra that is taking place. Maybe some linear algebra or some other form of algebra that force you that this sum of numbers, the number is always greater or equal than the size of X. So another way to put it, the same conjecture, if we add the quantities T1 bar up to Tm bar, and it's smaller than the size of X, then this means that there is a Tverberg point of order m plus 1. Okay, so if we write in this way, we can look at special cases. And the first special case of the cascade conjecture is precisely the radon theorem. If T1 bar of X is smaller than X, this means that X, the convex hull of X, the dimension of the convex hull of X is smaller than the size of X. The dimension of the convex hull of X plus 1 is smaller than the size of X. Then there is a radon point. Then there is a Tverberg partition to two parts. And this is precisely radon points. If we have more than D plus 2 points in dimension D, then there is a radon point. The second case is the simplest case where the conjecture is open. If we have a set of points, if we have a set of points, so that the dimension of the convex hull plus 1, plus the dimension of the radon point plus 1, all this together is smaller than the size of the set, then this means that we have a Tverberg point of order 3. Another way to say it is that suppose you have D plus 2 plus K points in RD. So if we have D plus 2 plus K points in RD, we expect that the radon points will be K-dimensional. And the conjecture says that if the points are in special position so that the radon points are only in K minus 1 dimension, then this implies that there is a Tverberg point. So this is about a configuration of points with less than the Tverberg number, 2D plus 3, which guarantee a Tverberg partition to 3. But if we have D plus 2 plus K points and the dimension of the radon points is smaller than K, then we have a Tverberg partition. Okay, so this case of the cascade conjecture implies Tverberg theorem for 3 parts, and it's unknown. It's very interesting. And so this conjecture, I think, was made by me in 74, so 50 years ago. And in the plane, it was proved by Akiva Kadari, but it's only available in Hebrew, and it's quite open in all other dimensions.
Gil, question?
Yes. Yes.
So when you say m equals 1 and m equals 2, is m the same thing as n? If you look back there, it looks like.
Here,
Yeah,
we have n points.
right.
Okay, let me go back. The conjecture, a formulation of a conjecture is that if we look at the
Oh, I see. Okay.
first m numbers, and if they sum up to something less than x, then there is a Tverberg point of order m plus 1.
Okay, sorry, I missed that.
Okay, and then this for m equal 1 is just Radon theorem. For m equal 2, it's already open. So this means that, and I stated it in a slightly different way. If we have d plus 2 plus k points in Rd, then either the Radon points are k-dimensional, which is what we expect in the general case, or there is a Tverberg point. Okay, so I should say that here is here is a topological speculative idea. Let's consider the complex of Radon partitions. We'll call it Radon, and this is the chain complex of the poset of Radon partitions. So we look at the Radon partitions ordered by inclusion, and we look at the chain complex. And actually, this comes from a very basic geometric construction. It is a polytope with a Z2 action, because we consider always when we have a Radon partition, we can replace the parts, and this is also a Radon partition. And and now we can consider the map from this complex to Rd. And this is a Z over 2Z equivariant map. And now the idea is to find a version of the Cascade conjecture, but a stronger version that for some topological index of F, if the index vanish, then this guarantee a Tverberg point to 3 partitions. So this is an idea. It's another topological idea related to Tverberg theorem, and I think it's an interesting to explore if anything like this is correct. And now I want to mention the following. Let G be a cubic graph with vertices 1 up to n. Associate to every edge ij the characteristic vector 1 in coordinate I and j, and 0 in all other coordinates. So this is the standard way to associate to a graph a configuration of points. This way, if we have a cubic graph, we have 3n over 2 points in Rn minus 1. So we have 3n minus 1 points in n minus 1 dimensional space. Why n minus 1 dimensional? Because the sum of coordinates in every point is 2. So they belong initially to Rn, but they all lie in a n minus 1 dimensional hyperplane. And then there is a very nice observation by Shmuel On, which says that the configuration has a Tverberg partition into 3 parts, if and only if the graph is 3-edge. No, I'm sorry, here, mistake, 3-edge colorable. Okay. Cannot move this. Okay. 3-edge colorable. Sorry about that. Oops. So this is an observation of Shmuel On, and this shows that if we don't have the Tverberg number, if we have a configuration of points below the Tverberg number, then the existence of Tverberg partition to 3 parts is an NP hard problem. And now the research project I propose is to study the complex of Radon partition and Radon points for configurations arising from planar and non-planar cubic graphs. And this, I think, would be interesting by itself. What can we say about this complex Radon, and what can we say about the map from from the radon partition to the radon points. And the speculative research idea is maybe there is a connection to the four-color theorem, namely, mainly there is some topological obstruction, some topological index that vanish for the radon point complex for all planar graphs. Like any speculative idea regarding the four-color theorem, one place to start is not to consider planar graph, but to consider bipartite cubic graph. For bipartite cubic graph, the assertion that there are three edge colorable is very simple, and it would be a nice sub-project to understand the radon partition of bipartite cubic graphs. Okay, so this was about the cascade conjecture and some speculation about connection to topology and to the four-color theorem. And now I want to move to a problem that surprisingly I didn't encounter before, and this is a question about the maximum number of Third partition. So we have a nice conjecture about the minimum number of Third partition, which is wide open, but what about the maximum? So here, I don't know the answer. I was surprised that this question was not asked until very recently. And there is a nice argument, which perhaps for a slight version of the problem, show that the maximum is exponentially bigger than the minimum. And it's based on the following idea. You start with Gaussian points in RD. You want to ask how many Tverber points there are. Let's say that we talk about linear Tverber points, that we don't care about convex hull, about what's called positive hulls. This is why we take d times r minus 1 plus 1. In this case, there are a configuration where the number of, when this number will be 0, but we can prove that the expected number is this, is satisfied by this expression, 1 over r factorial d choose d over 2 to the power of m. And the reason is that we can talk, instead of talking about Tverber point, we can talk about Tverber points with signs, where we talk about linear combination, but we don't decide that all the linear combinations are positive, but we prescribe the signs for every vertex, and there are 2 to the m prescription for the signs, but because of symmetry, the number of so-called Tverber partition with signs will be the same. The expected number will be the same for every prescription of signs. And therefore, the number which corresponds to the genuine Tverber partition will be at least this expression, d over 2 to the power of m times 1 over r factorial. So there is a c to the m gap, where c is greater or equal to e over 2, between the conjectured minimum and the expectation. And one can speculate that maybe the maximum is equal to the expectation. I don't have a clue about the maximum, and I'm only surprised that this question was not asked before about the Tverber partition. So now I want to, toward the end of the proof, I want to move. I already here mentioned Gaussian points in RD. I want to mention some work about how the radon points and Tverber points behave for Gaussian configuration of points. I think Gaussian configuration of points is very interesting model. It's often simpler than other models. And here, let me mention to you a problem that you probably heard about, which is, this is Sylvester problem. Let K be a convex body in the plane. What is the probability that the convex hull of 4 randomly distributed points of K are in convex positions? And he published this question in 1865. A year later, he published a more vague version that people didn't understand so well. Then this is also a bit vague, because it's not clear what does it mean 4 randomly distributed Okay, this is less vague, I'm sorry. And this is a question he asked, and there is a lot of literature about this question. Sylvester was a very interesting person. Probably you heard about the Kalai-Sylvester theorem. When you read about Sylvester, the striking thing about Sylvester that his life was quite similar to our life. So probably he didn't have a laptop, he didn't have computer, he didn't have cell phone, but his trajectory of life was similar. You know, he did a PhD, he tried to find a job, he moved to this university, then to make a little more money, he consulted in the high tech of the time, some insurance company, then he moved to the United States, he moved back. Very similar life to our life. So maybe mathematics is a place where you find the fixed point of life. Certainly the problems remain fairly stable along the year because of our failure to solve them. In any case, it's interesting to ask both analytically and experimentally questions about Gaussian random points. And let me mention one result. So the big question is what can be said about Radon and Weber partitions for Gaussian random points. And one thing that was proved by this group, so Sui Hong Chan and al. So Trion Chang, myself, Baragav Narayan, Natasha Tersakov, and Moshe White, is that if we consider d plus 2 points, and we ask what is the probability that the partition to the first k point and the last d plus 2 minus k point is a Radon partition, and it turns out this probability is unimodal. In fact, it's even log concave. And this is a nice result. It's not as hard as the recent log concavity result, but it's not at all easy. So I want to conclude by telling you some experiment. I don't know if it's called experimental problem, but one thing we did, we all know that for 4 points in the plane, there are two types of configuration as far as the Radon points. Either they are in convex position or they are not in convex position. And it turns out that for 7 points in R2, which is a Tverberg number for 3 parts, there are 11 configurations. And there is some way to move from one to another, which comes from a work of Imre Barani. And by computer experimentation, we find all this configuration. We found the number of Tverberg partitions, and we found also what is the probability in the Gaussian model to get this type of configuration. So these are the types. Here you have a 7 Tverberg partition, which is the maximum, and 4 Tverberg partition is the minimum. What happened for 9 points in R3? So here I cannot tell you anything definite, but I can tell you what we got. And I don't know, I'm fond of it that we did this and so on. And we ran 10 million trials of 9 points in dimension 3 with the Gaussian models. And we found about 2 million that had 8 partitions. So 8 partition is the minimum. We didn't find anything which is below the conjectural minimum, which is, well, you always like to disprove conjectures, but we didn't disprove the conjecture. And then we found a various configuration with more partition. The record was, we found 3 trials with 19 partitions. Since the number is 3, is so small, it's quite possible that there are even a configuration with more partitions than 3. And there was okay, let me not show you further experimentation, but I think it's very interesting to try to understand, to make sense of this data. In the case of 7 points, I said that the computer experimentation clearly showed that there are 11 configurations, and I think now we completed a proof that this is indeed the case. Here, I think we can only hope for experimental data, and I don't know, I like it, and it's interesting how to get sense of it and what to do about it. So let me just, oops, what happened? Oh, okay, so let me finish here, and thank you very much. And I'll stop share. And it's a pleasure again to see you all and to be in the Northwest US. And I hope that everything will turn to better, both in the global events and in your lives. And thank you very much.
Does anybody have any questions? You can just jump in, I think.
I wanted to ask for clarification when you mentioned the points being distributed based on Gaussian randomness. Is that like independent in each dimension, normally distributed?
Yes, independent in each dimension. So each coordinate is Gaussian, and all the random variables are statistically independent. Yes.
And the mean is always the origin, probably, or
Yeah.
Are there other questions? While we wait, I have a silly one. How did the name of the Cascade Conjecture come about? Does it have anything to do with the Pacific Northwest?
No, I think it doesn't have anything to do with the Pacific Coast. I don't remember. So certainly I didn't call it the Cascade Conjecture. And at some point, people, maybe the name was offered by Karima Di Parzito at some point, but I'm not entirely sure about it.
Okay.
But this is,
It is fitting here. Any other real questions or silly ones?
Yeah,
I encourage silly questions, yes.
I have a question that displays my lack of understanding of everything here. That you mentioned the connection to the four-color theorem. Is there any statement you could phrase in terms of like random graphs? Since you had a Gaussian distribution of points here, is there anything you could translate into like random graphs and then colorability of those?
I don't know. So certainly, well, I don't, you see, random cubic graphs are very complicated objects. I think random cubic graphs, some of them are three colorable, some of them are four colorable, four edge colorable. So I don't think randomness enter into this speculation. So this speculation is sufficiently far-fetched, if I may say so. But I remember with Eric Babson, I think in the 90s, we tried to look at radon points of configuration coming from cubic graphs, and it looks very interesting, very interesting things to explore, regardless of the four-color theorem. So I think it's an interesting research project.
Great. By the way, I'm gonna in the middle of the questions, I'm gonna share screen. Can you see this now? A poster for this spring. There will be a Cascade Lectures in Combinatorics March 8th in Seattle. I just wanted to remember to do that, but and I'll leave that up now. Are there any further questions?
There's a question in the chat.
Yeah.
Okay, I can't see it now.
I can. Or it's Ben Young asks, sorry, I'm having computer issues, so audio is not good. What evidence is there in favor of the Cascade Conjecture?
So as I said, it is known for the plane. You can replace let's say you replace the Tverber point by you can replace the Tverberg point of order R by the intersection of all the convex hull of the points when you delete R minus one of them. So you look at all the intersection of convex hull when you delete R minus one points, and this is called the R core of the set, and this is always bigger. It always contains the Tverberg point, and as a matter of fact, Akiva Kadari used this for his proof in the plane, and it's known that for the R core, if you sum the dimension, it is correct. Beside that, evidence. It's a good question. Yeah, I don't know. I think it's just I just find it elegant conjecture that I refuse to think about the possibility it's incorrect, but often elegant conjectures are incorrect. So maybe it's a good idea to try to find a counterexample.
Other questions?
Just another follow-up comment by Ben Young in response to the question. Thank you. Also, non-substantial comment. Your empirical data appears to be log concave, except possibly in low dimension.
Which empirical? What is? I don't understand the question. What is log concave?
A sequence based on number of partitions at the end, maybe?
That's a good question, you see. This is a good question. I didn't think about it. Well, let's say even before log concave, whether it's unimodal. So for 9 points in R3, the number of partition, wait, it looks unimodal. I don't know if to conjecture that.
But if you do ever conjecture that, it could be the CALICO conjecture.
Okay. If it's going to be the CALICO conjecture, maybe I go ahead and conjecture it.
Any other questions or comments? Well, while we're thinking a second, I forgot to say for the spring meeting that there is travel funding for young people to apply. They can go to there's a conference website and that will list that, and I'll send out announcements. But sorry to be interspersing this with the questions, but it gives you more time to think. Any more questions? If not, let's thank Gil again. And the